Good evening. I am Richard Davenport, President of Minnesota State University, Mankato. And I am pleased this evening to welcome you to the 46th Annual Douglas R. Moore Faculty Research Lecture. The Douglas R. Moore Faculty Research Lectureship Award honors a faculty member who has engaged in an activity that demonstrates a quality of excellence in discovery and provides a venue for sharing that knowledge in a manner that enriches the intellectual life of the university community. So tonight, I am pleased to introduce the recipient of the 2020 award, Dr. Shu-Wan-Wee Wu. Dr. Wu is an associate professor in the Department of Electrical and Computer Engineering and Technology. His research has the potential to transform the way we use 5G technology in our smartphones and also explores developments related to high-capacity antennas. I'm looking forward to learning more about how his intellectual inspiration was translated into a prototype in the lab. So everyone, please join me in welcoming Dr. Wu. His presentation is titled Antenna Technology for 5G and Beyond Systems. From a concept of inspiration on scratch paper to prototypes in the lab. Dr. Wu.
Hello everyone, thanks for attending my talk. My talk tonight is the creation of a novel antenna technology for 5G and beyond systems. This research is carried out by me and my graduate students in the recent years. First, let me give you a brief introduction of the history of mobile technology. The first wireless telephone service was open to the public in 1926. That was offered by the German company, the German National Railway, on a route between Berlin and Hamburg, and is only serviced to first-class passengers. In 1956, the mobile phone for private vehicle was put on the market in Sweden. However, the equipment is very heavy. It weighs 88 pounds and only serviced 125 subscribers. Our first handheld phone was introduced in 1973. That actually is a prototype. Okay, it's called Dynatech. It weighs 2.5 pounds, and it was invented by Dr. Martin Cooper from Motorola. And this photo was taken in 2007. I remember, if I remember correctly. Okay. However, the prototype was invented in 1973, but it took Motorola design team another 9 years to commercialize this product. Okay, so we call this is the first generation mobile technology. And that time, only the analog voice can be served. Okay, there is no text message. The second generation started service in 1992. And digital modulation was introduced at that time. So the data rate is 40K bit per second. And the third system into service. And the data rate is much higher, goes to 3 megabit per second. And in 2012, this is a system which is most popular nowadays. We call it 4G systems. The data rate is 60 megabit per second. Now we're talking about 5G. 5G started to introduce into market in last year, 2019, and it's supposed to finish deployment at the end of this year, 2020. And the data rate is supposed to be very high, 2 gigahertz to 10 gigahertz bit per second. And in last year, people start talking about the 6G, and we don't know when will that happen. Based on the history, you can check you can find out every 10 years, we get into a new generation. So we expect the 6G will appear in 2030s. Actually, FCC opened a very broad spectrum for the experimental research of the 6G systems. That spectrum is 95 gigahertz, goes up to 3,000 gigahertz. That is a huge bandwidth. Now here I want to point out the 5G system is not just the cell phone industry, okay? Of course, the cell phone is the biggest industry for 5G. The second largest market is autonomous vehicles. For autonomous driving, all those vehicles has a lot of sensors, and those sensors have to implement wireless communication between them, and also the wireless communication between different vehicles. So the high data rate is required by autonomous vehicles can be implemented by 5G. And eventually, engineers can implement the wireless connection of everything. That is the concept called Internet of the Things. In last year, there is a research report. It says the 5G already had a global market of $43 billion in 2018, and it will grow to $700 billion by 2030. Now let's talk about the importance of antennas. The antenna looks very simple, but is very important component. It always is the bottleneck of a wireless communication systems. So this photo, I put Steve Jobs. Everyone knows him. He's very famous. So on June 7th of 2010, this is when the photo took. Okay, Steve Jobs introduced iPhone 4 on the Apple Developer Conference in San Francisco. Okay, a couple of days later, there's a customer and find some problems. Then he sent an email to the Steve Jobs. His problem is basically that customer is a left-handed person. When he used the left hand to hold that iPhone 4, the network drops. So he asked Steve Jobs, is there any solutions? The Steve Jobs replied to him on the same day. He said, this is a fact of life of every wireless phones. And he suggests him either to purchase a case, solve the problems, or try not to grab the phone on the lower left corners. Of course, this customer is not very happy with these solutions, so he posts the email on the internet, and I dig it up and post it here. So my point here is determines the quality of the received signals before any advanced signal processing algorithms is applied. So no matter how powerful the processor you use on your phone, or how friendly the interface you have on your phone, if your antenna fails, then your cell phone fails. Unfortunately, the advance of antenna technology is much slower than other electronic devices. This is mainly because you have less design degree of freedom for the antennas. For other electronic devices, you can play with the material. You can control where the signal is propagating. You can use the ceramic or use the plastic or other type of the fancy materials. But for antennas, the signal must be in the free space, and you cannot change free space. So that gives a lot of the design limitations to antenna engineers. Now let's talk about what is the design challenges for the 5G or beyond systems. First, I give you a table here. This for different generation of mobile technology. For 2G, the carrier frequency is 1.9 gigahertz. For 3G, the carrier frequency is 2.1 gigahertz. The 4G, the frequency is 5.2 gigahertz. For the 5G, the carrier frequency goes up to 39 gigahertz. So why we always increase the carrier frequencies? Because we need more bandwidth. More bandwidth is required by more data rate. Now I will show you that more bandwidth is available at a higher carrier frequency due to the frequency scaling property of antennas. I just give you a very simple examples. So on the left-hand side, I give you a patch antenna. Suppose this antenna operating from 1 gigahertz to 1.1 gigahertz. So the bandwidth is 100 megahertz. Using the frequency scaling, if we divide every dimension of this antenna by 2, so the antenna size will shrink, okay? Then operating frequency of the antenna will go up with a factor of 2. So the smaller version of the antenna will operating from 2 gigahertz to 2.2 gigahertz, and we achieve 200 megahertz bandwidth. So this example tells us when we increase operating bandwidth, we can get more when we increase the frequency of the antennas, operating frequency of the antennas, we can get more bandwidth. Now let's take a look of the circuit of a cell phone. So this is iPhone, okay? Someone open iPhone and take photo of the inside circuit. You can see this is very complicated printed circuit board with hundreds of the components. If you look details of the circuit board, you're going to find out there are a lot of the trays. They have very close located copper trays, okay? Like those trays, they are very closely located. Now, at very high frequencies, for example, 39 gigahertz, okay? Those trays has very high thermal loss and very high radiation loss. And also, you will have signal crosstalk. So what is the signal crosstalk? Signal crosstalk means the signal will jump between the lines. I will give you one example here. So this is a printed circuit board with 2 separated copper trays. The trace 1 connects terminal 1 and terminal 2. Another tray is connected to terminal 3. These 2 trays, they are disconnected. Okay, so there is no connection between these 2 trays. So if we connect the signal source to excite terminal 1, it can be expected the signal will coming out of terminal 2, but not terminal 3, right? Because these 2 lines. However, when the frequency of the signal source is high, this is what you are going to see. Okay, so this animation shows the propagation of the signal on this signal. Although a lot of signals does coming from terminal 1 to terminal 2, but there is a significant amount of signals also get out of terminal 3. So when you design the circuit at high frequencies, you are going to find out those signals on different trays, they will jump between different signal lines, which is not good. The copper trays on circuit board is inefficient to carry signals at a millimeter wave frequency when the frequency is very high. So what is the solutions? Okay, people trying to find out the solutions to look at another type of circuit. Some of you may not familiar. So this is waveguide type of circuit. Okay. Normally, this type of circuit is used for mission critical applications. And a waveguide is basically a piece of hollow metals. Okay, and the signal just propagates in the hollow channels. Now, for the waveguide circuit, the thermal loss is very low, because it's just air inside the channel. There's no material loss, and there is almost no radiation loss because the waveguide itself is an enclosed structure. There's no opening, so the energy cannot leaks out. And also there is no signal crosstalk between the neighboring waveguides because they are totally isolated physically. So there's a big performance gap between the printed circuit board based device and waveguide based device. And if we can design a new type of circuit whose performance is between these two, maybe we can get some benefit from the printed circuit board and we can get some benefit from the waveguide. So Canada who invent a new technology to solving these problems. And this paper is very, very famous, okay? Until last week, the citation is 833, which is very high in the antenna areas. So their idea is they can implement a conventional waveguide on a piece of printed circuit board, a double-sided printed circuit board. So we can see like a waveguide has 4 metal walls, 2 horizontal walls, and 2 vertical walls. A printed circuit board comes with 2 horizontal walls, but there is no vertical walls. So that research group, they drill 2 rows of holes and metallize the surface of those holes. And the 2 rows of holes can emulate as the 2 vertical walls. And this is the simulation of the signal propagate on the inside. And they give us almost identical field distribution. So it tells us the new structure made on the printed circuit board can be used to replace the conventional waveguide. Okay. And they use this concept to design. They give a name to this waveguide on printed circuit board. It's called substrate integrated waveguide. So here I give you some examples of conventional waveguide structure and some examples of the substrate integrated waveguide devices. Okay, the short term is called SIEW. Now, obviously, the conventional waveguide device has very good performance, but it's bulky, heavy to make. However, the SIEW device is relatively cheap. It's low cost, okay, because it's made on printed circuit board, and the size is compact. It's lightweight. The performance is not as good as the conventional waveguide devices, but we have acceptable performance. The performance will be better than a copper trace-based printed circuit board devices. Now, since the SIEW device is the waveguide implementation on the waveguide implementation on the printed circuit board, so it's better we take a look at the traditional 2-dimensional waveguide structures. Okay. Now here I put 2 types of waveguide devices. They both are 2D planar structure because they have constant height. The first one is we call it H band. The second one we call it E band. Although they look very similar, but actually they are different devices. Their electrical performance is totally different. Okay, what's the difference between these two? The difference is the direction of the electrical field and magnetic field. Okay, so for a waveguide, the electrical field, the direction of the electrical field is always pointing from the long wall to the long wall. Okay, so the red arrow here is the electrical field direction, and magnetic field is perpendicular to the electrical field. So in this case, the magnetic field is from the short wall to the short wall. So for the first H band, we can find out is the magnetic field direction is parallel to the 2D planar structure. So we call this is H-plane type of device. And the second one is the electrical field is parallel to the 2D structure. We call it E-plane type of device. The simplest waveguide structure for the E-plane and H-plane device is just a piece of waveguide. So this waveguide, when we put this long wall on the horizontal planes, this is considered as H-plane type of waveguide. And we already demonstrated that this waveguide can be implemented on printed circuit board by the SIEW technology. The field distribution, they are identical. But when I read those hundreds of the literatures used, I find out all of them are about the design of H type of circuit. None of them come up with the design of E-type of circuit. Then it raised me a question like, why no one ever invented an E-type of circuit using SIEW? So I tried to see whether the SIEW is efficiently to guide the signals for the E-type of the circuit. So when we flip the waveguide 90 degrees, then this waveguide becomes E-type of circuit because the electrical field is parallel to the horizontal plane. Then we use the plated through holes to emulate the vertical walls in this case. So this vertical wall in this case is long wall, it's not short wall anymore. Then simulation results tells us it fails. Okay, so this field distribution tells you the signal propagation inside this conventional waveguide. And this field distribution tells you the signal will not be guided by your SIEW structure. Instead, it will just radiate as if those posts does not exist. Then it comes up to me the question, why it behave like this? My first thought is maybe the gap between the holes are too big. So I decrease the gap between holes. It doesn't work. And my second thought is maybe the holes are large. So I decrease the size of holes and it still doesn't work. Then I realized the SIEW proposed by the Canadian research group is an incomplete solution. It can only be used to design H-plane, but not E-plane type of circuit. So I was very confused, okay? How do we solve these problems? Because in the real life, actually, when you look into the those 2D waveguide circuits on the market, actually there are more E-plane type of devices than H-plane type of devices, because the E-plane type of devices normally give you a more compact design and more broad bandwidth. So one day, when I was in a restaurant having a lunch, some of you may already recognize this restaurant. This is actually the noodle company in the University Square, okay? I draw some current distributions guide at the back of a receipt of the noodle company. Of course, I already lost that receipt, so I redraw those drawings on a piece of paper to show you. So those arrow and the lines, let me see, where's my mouse? Those arrow and the lines tells you the current distribution on conventional waveguide. Okay, so this waveguide is considered as H-plane waveguide because the E field direction is perpendicular to the horizontal planes. Okay, and this waveguide we simply flipped original waveguide 90 degrees. So this is considered as H-plane waveguide because the E field is parallel to the horizontal planes. Now, what I found is for the H-plane waveguides, on the two vertical walls, you only have vertical directed E field, vertical directed current. And this explains why the SIEW succeeds to design H-plane waveguide, because those copper plated through holes is able to support the vertical directed current. However, in the E-plane case, those vias only support the vertical component of current. But now on these vertical walls, you see, we not only have vertical directed current, we also have we call this longitudinal directed current. This current is along the propagation direction of the component cannot be supported by those vias because those vias are disconnected in this direction. Okay, so this is idea. This is phenomenon I found, and I believe this is the reason why SIEW fail in the E-plane waveguide cases. Then I go back, I trying to solving a more general circuit, because eventually we're not only interested into a simple waveguide. What we're interested is an arbitrary shaped 2D circuit. So here I gave you an arbitrary 2D circuit. The first one is H-plane waveguide, where the E field is perpendicular to the planar structure. And the second one is E-plane circuit, where the E field is to the E field structure. Okay. So we can mathematically prove. Okay, to get the same conclusion as the previous slides. So the proof will start from the Maxwell equations. Okay, this Maxwell, this is only slide I have some mathematical equations. Okay, so bear with me. So if you still remember the calculus in college, you can solving this Maxwell equation under these two devices, and I just give you a solution here. So for the H-plane circuit, we can find out the L directed current equals to 0. Okay, the Z directed current is not equals to 0. So that is why the SIEW concept works, because those vias is able to support JZ, and we don't need any feature to support JL because JL equals to 0. So that's why this concept works. But for the E-plane waveguide circuit, you see, for this circuit itself, this support JZ could be non-zero, but JL must be 0 in this structure because there's no feature to support JL. So that is why this doesn't work. So our conclusion is the copper plated through holes only support vertical current JZ, but not longitudinal current JL. And H-plane circuit only have non-zero JZ, so SIEW will succeed. The E-plane circuit has both non-zero JZ and non-zero JL, so SIEW will fail. Now we find the problems. How can we solve it? Okay, the idea actually is pretty straightforward. Since the failure of the SIEW in the E-plane circuit is because there is no feature to support the flowing of the longitudinal current. So if we add some feature to support the flowing of that current, then the design, we insert copper strip at the middle height of the circuit along the boundary of the circuit. Okay, and we still keep those plated through holes. So the vertical current JZ can still be supported by those plated through holes. And JL, okay, the longitudinal current JL will be supported by the inserted copper strip. So this should work, right? But we need to verify that. So first we verify that by simulations. We first build a model of the, actually we call this new structure is substrate integrated E-plane waveguide, SIEW, okay? Versus the previous structure is called SIW. So the new structure is SIEW. So we modeled a section of SIEW softwares, and this is the result we get. So the excited field, E field direction is horizontal, and the signal is successfully guided from one terminal to the other terminals. Not like the previous case, the signal just radiates as if the post does not exist. Another good feature of this structure we found out is the SIEW can also be considered as H-plane waveguide to support a vertical polarized field. So if the E field is fully polarized, then the distribution of the signal is exactly the same as the conventional waveguide and also the same as the SIEW. So now we have a complete solution. Unlike SIEW that only guides vertical electrical signals, the newly proposed SIEW guides both vertical and horizontal electrical field. It offers a complete solution to design waveguide devices on a printed circuit board. Next, we will verify this experimentally. Okay, then we use this new structure to design a couple novel antennas. So this slide is talking about the experimental validations. Okay, as engineers, the simulation validation is not enough. We need to build a prototype and do measurement to make sure the concept works. So this is the empty SIEW prototype we made. It made of 2 pieces of printed circuit board. Okay. So we actually stack these 2 boards face to face, and bake in the toast oven to get the final prototype. Okay. Now, one feature details I like to emphasize is there are very fine features at here. Okay, so this portion is for the connection of the testing equipment to our device. We call this the SMA adapters. Okay. Now, the point I want to emphasize is the design at high frequency is very different to the design at low frequencies. At low frequency, we only concern the circuits are connected or disconnected. Okay, we don't worry about the shape of the trace. We don't worry about the width of the trace. But at microwave frequency, every dimension is very important. If you change any number here, the performance will drop dramatically. Okay, so this part, as I mentioned, this is called the connectors, because the SIEW we invented is not a standard structure. It cannot be interfaced directly to the test equipment. So like this is cable of the test equipment. We have to, in order to connect the cable to our device, we need to build these transitions. So this is measured result. Okay, so these 2 lines, one is simulation, one is measurement, tells you the transmission coefficient. So this tells you the percentage of the power transmitted from one port to another port. Okay, the y-axis, this is in decibel scale. So when you convert this into percentage, this is about -1 dB. This is will give you about 80%. So that means 80% of the power will transmit it from port 1 to port 2, which is very good. And these 2 lines tells you the reflection coefficient. This tells you how the percentage of power reflected at the input port. Normally, we check the spec line of -10 dB. Okay, if it's less than -10 dB, we consider that is good. The -10 dB means 10% of the power is reflected. So by doing this experiment, we prove our concept of SIEW is correct. Now let's come to the design of antennas. The first antenna we design is the SIEW horn antennas. Okay, again, this is made of two pieces of printed circuit board. So here I show you the baking process, a photo of the baking structure used the baking process in the toast oven. Okay, we clamp the 2 boards and bake in the toast oven. When the temperature reaches about 400 Fahrenheit, which is the melting point of the solders, we turn off the oven and let it cure and cool down. So here is the distribution. Okay, from here it's very easy to find out the field generated by this antenna is horizontally polarized, which cannot be achieved by the traditional SIEW structure. Okay, and you can tell from this colored figure, the energy is propagated from the coaxial port and radiates into the free space. And we also measure the reflection coefficient. When we draw these -10 dB lines, we can find out what is the operating bandwidth. The operating bandwidth, it looks like it's from 16.9 gigahertz to somewhere 18.3 gigahertz. Okay, so it's more than 1 gigahertz bandwidth. Now this is antenna, so we also need to measure the radiation characteristic of the antenna. Now we measure, for any measurement of the radiation characteristic, we have to measure in an anechoic chamber. Okay, I will have a separate slide to discuss these chambers. So this plot basically tells you the radiation or or reception capability of your antenna with respect to angle, with respect to different directions. So horizontal axis is the different directions. Vertical axis is the receiving capability. Now let's take a look of this lady. This lady, what is this lady doing? This lady is looking for antenna signals, looking for cell phone signals. Okay, so when you have a very weak signals, normally there are two options to solving the problems to boost your signals. One is you increase the signal power, okay, the transmitting power. But increasing transmitting power is a very expensive solutions. Normally people don't choose that. Another way is you can use antenna array to increase reception capability of your signals. Okay, so this is antenna arrays. So basically, you can consider there are two set of the two antennas. They put side by side, and the signal received by the two antennas will combine together and collected by this port. Okay, so we can tell the receiving capability of this array is better than the receiving capability of the single elements by compare the radiation patterns. So the first pattern here, this gives you the radiation pattern of single element. This gives you the radiation pattern of the two element arrays. What's the difference? The difference is this pattern, this radiation beam is much narrower than this radiation beam. This is wider, this is narrower. So if you consider your antenna as a transmitting mode, for example, you're transmitting signals using your antennas, then the narrow beam means you can transmit your signal in a more focused way. So you focus most of your energy in a certain directions. While in this case, your energy is somehow spread out. So when you more focus your energy in a certain directions, then at the receiving side, you're going to receive more signals. Another way to compare the single element and the 2D and two element array is we can compare the antenna gain values. So antenna gain value is actually a quantitative evaluation of the reception capability of antennas. So the higher the value is, the more reception capability the antenna is. So the solid line here is for the array. The dotted line here is for single element. And there are 3 dB difference. So when you convert 3 dB back into the magnitude, that means the antenna array has the reception capability of the array is double of the reception capability of the single element. Okay, that is the 3 dB means. So this publication published this work on IEEE transactions on antennas and propagation. Now, second design I will present to you is a dual polarized antennas. So what is dual polarized antennas? And we know antenna, we transmit signals on different frequencies, and frequency is a natural resources. We would like to make fully use of the resources. We don't want to waste our resources, okay? So electromagnetic wave has its polarizations. That means is the direction of the electrical field. So in the 3D space, okay, you have two, the wave is always perpendicular to the propagation direction. So you have two degree of freedoms. One is horizontal, one is vertical, okay? So at the same frequency, actually two independent signals at the same frequency, one horizontally and one vertically directed, can be transmitted or received simultaneously. So you use the same frequency twice, right? So you double the use. So this is the structure we designed. Now this antenna, it has two separate ports. You can find out two separate ports. So this port, we call it vertical port because it will generate vertically polarized E field. And this port we call horizontal port because it will generate horizontally polarized E field. Okay. Again, we use the same baking process to build this prototype. If you find vertical port, you can tell the signals coming from this port and get into this OMT structure and radiated by these antennas. And this is the directional field if you look into this antenna from these directions. So you can find out the field is vertical directed. And if you excite this horizontal part, then energy flowing from these directions, okay, get into the horn sections and radiated. And again, the electrical field will be horizontally directed. Now, these two field components, they are orthogonal, so there will be no interference. And at the receiving side, if you use the same antenna to receive, then the vertical signal will only be received by the vertical part at the receiving side. And the horizontal signals will only be received by the horizontal side, horizontal part of the receiving signals. Then you can separate the two data streams. And we published this result again on IEEE on antennas and propagations. So some measurement result of these dual polarized antennas, okay? So this is the S parameters. Now, different to the previous antennas, now this antenna has two ports. So we are going to measure more curves. Basically, there are three curves we need to measure. The reflection coefficient for the horizontal part and reflection coefficient for the vertical part. So these two reflection coefficients have a similar physical meaning as the previous antennas. But there is another curve called coupling coefficient, which is S21. That means when you excite port 1, when you excite vertical port, how much energy will come out from horizontal port, okay? So that is this dot here, this dot line here. So for the coupling, normally the standard spec is minus 20 dB, okay? So minus 20 dB, that means 1% of power is coupled from vertical port to horizontal port. So our design here is below the minus 20 dB, which is good. And for the reflection coefficient for both two ports, the spec line is this red line is minus 10 dB. So everything below this minus 10 dB line is good. The measurement of the radiation pattern is the similar as before, okay? We measure this in the same setup in anechoic chambers, okay? For the radiation pattern measurement, we must carry out in anechoic chamber because we have to eliminate the reflection due to the reflection of the signals coming from the ceilings, coming from the floor, coming from the walls. Okay, I have a separate slide to give you more details. Now, the last design I would like to share with you is a very interesting design, which is called a circularly polarized antenna. The circularly polarized antenna is able to generate electrical field, which is spinning over the time. Now, this is the design, okay? Although this design looks very similar to the previous SIEW horn antenna single element, but actually they are different, okay? When you look into the details of this structure, so here I show you the three-dimensional geometry of the connectors, you'll find out there is an extra piece of the copper cylinder here, okay? So this cylinder will generate actually the vertical directed field. So if you don't have this cylinder, without this cylinder, you only have horizontal E field. Now we add this cylinder, you have vertical E field. As I explained before, the SIEW structure we invented here is support both vertical and horizontal E field. So that means both the vertical and horizontal field generated by this adapter will propagate along the structure, okay, along our antenna. However, the propagation speed of these two components is different. The horizontal field runs slower, the vertical field runs fast. So they run at a different speed. So you are going to achieve a phase difference when the signals get into the free space, okay? When we carefully design our structure to achieve the phase difference is 90 degrees, then you are going to achieve a spinning type of the field, okay? You see from here, we can tell the electrical field direction is spinning counterclockwise. But in the antenna areas, we don't use the term clockwise or counterclockwise because the clockwise or counterclockwise, it depends on how do you look at it. when you look at these animations, you may say this is counterclockwise. But if you look at this clockwise. So instead of using clockwise or counterclockwise to describe the spinning of the directions, we use a personal hand. Okay, so you use 4 fingers to point into the spinning of the E field, and some to point into the propagation, signal propagation directions. If your radiation field is consistent to your left hand, we call this is a left-hand CP antenna. So the short term is LHCP, left-hand CP. Okay. Otherwise, that is a right-hand CP. So we also designed a right-hand CP. So this is right-hand CP antennas. What's the difference between these 2 antennas? Okay. So for this right-hand CP, we introduced the additional copper strip at the middle layers. These copper strips will have no effect on the vertical polarizations. So the vertical polarization will run at the same speed. It will drag the propagation of the horizontal field. So the horizontal field will run even slower. Okay, why is that? Because electromagnetic wave has a very interesting feature. If you insert metals, okay, if the metal surface is perpendicular to your E field, then your metal surface will not disturb the E field, the electrical field. However, if your metal surface is parallel to the electrical field, then you are going to significantly affect the electrical field. Okay, so that is the reason. Now, this turtle runs even slower, like it's like walking, it's not running, like this turtle is still running, right? But it runs smaller than this rabbit. So this turtle runs even slower. So the difference of the speed between the 2 wave components is even larger. Then if you carefully design those steps such that you can achieve 270-degree phase difference in the airs for signals, then you can get the right-hand side CP. Okay, so we can find out in this case the spinning of the E field is opposite to of the other field. Okay, so we designed a circular polarized antenna. But let's see, we need a quantitative evaluation of how good your CP antenna is. Now let me ask you a question. Okay, how circular is a circle? This seems a weird question, right? So is this a circle? It looks like this is a very good circles. So how about this one? Is this a circle? You may say this is a circle, or maybe this is an oval. How about this one? This definitely is not a circle. It is an oval. But if you ask the same question to an antenna engineer, they will say they are all circles. But the first one is a perfect circle. The second one is a good circle. The last one is a poor circle. So how do we quantitatively tell which one is perfect, which one is good, which one is poor? There's a parameter called actual ratio. So actual ratio is defined as the maximum radius divided by the minimum radius. So if you use this number, you can find out for a perfect circle, the actual ratio equals to 1 because the radius is constant for a perfect circle. Okay, and if the actual ratio is less than square root of 2, we call that is a good circle. And if the actual ratio is larger than square root of 2, we call that as a poor circle. So after you build the prototype, how do you measure the actual ratio? Actual ratio is very important parameters for CP antennas. So actually, you need a linear polarized antenna to measure the actual. Let's say this linear polarized antennas, there is a rotator installed at the back of the antenna, so this antenna is able to spin. Okay. So when the antenna spins, the direction of E field of this antenna is pointing from this long edge to this long edge. When the antenna spins, the direction of E field will spin, right? Will rotate. When the direction of E field aligns to the long axis of this oval, then you get the maximum signal. When the direction of the E field aligned to the short axis of this oval, you get the minimum signal. Okay, so in the measurements, you just manually or automatically turn this linear polarized antenna 360 degrees. You record the maximum value and you record the minimum value. You divide these two values, you get actual ratio. So this is what we did to measure the actual ratio of our antennas. We have simulation result and measurement result. Now, actual ratio, the standard is 3 dB. So we draw a line of 3 dB here. Everything below 3 dB is good. Everything above 3 dB is bad. Okay. So 3 dB, when you convert into amplitude, is actually equals to square root of 2. So that is why we use square root of 2 as a reference. Now, we can measure the reflection coefficient of the two antennas, and we can measure the radiation patterns of the two antennas. Now, this is last slide. Okay, let me talk about the measurement of the radiation performance. Now, for the measurement of the antennas, there are 3 types of measurement. The first one is the radiation pattern measurement. That gives you the radiation capability of the antenna with respect to different angles. The second one is antenna gain measurement. That gives you an absolute value to describe the receiving capability of your antenna or transmitting capability. The last one is actual ratio measurement for CP antennas. Now, I like to point out here is antenna is a radiation structure. The signals goes everywhere, right? So in order to eliminate the interference from the other radiations or the interference from the ground refraction or the wall reflections, we have to measure the radiation characteristics in anechoic chambers. Okay, so here I will play a short video. And for measurement setup. Wait a moment. Okay. This is the antenna lab. We have 2 major pieces of equipment here. One is this big metal box. This is called anechoic chamber. Another one is this machine, which is called vector network analyzer. The metal box is able to isolate the antenna testing environment from the outside, and this equipment will basically get the data from measurements. Okay. Let's take a look of inside of this box. So inside of this box, we have a lot of the cone-shaped material installed. They installed on the floor, installed on the wall, and also installed on ceilings. Okay, so the function of those materials is to absorb all the radiation generated by the antenna inside these rooms. And also, because this entire box is enclosed with metal materials, so outside radiation will not get in once all the doors are closed. So we put 2 antennas inside this room, one for transmitting, one for receiving. Okay, so on each side of the room. Okay, so on one side, what we put here is a broadband double ridge horn antennas. Okay, it's able to generate the broadband signals. Now let's check the other side. Okay, there's no door for the other side, but there is a small hole we can crawl inside. Okay, let's go take a look. So we put a tripod here, and on the tripod we installed a rotator. Okay, this rotator is able to spin. Okay, the rotation of this rotator is automatically controlled by a computers. Okay, then I put the SIEW horn antenna array here for the measurement. So this is the antenna we're trying to measure, and that one is the signal source. Okay, so there are a total of 3 different types of the antenna radiation performance measurement. I will explain one by one. Okay, the first one is the antenna gain measurement. So in order to measure the gain of our design antennas, we need to measure the system twice. The first time we need to measure a standard gain horn. So this is a standard gain horn. This is a standard used as a reference. So we replace our antennas using this standard gain horn and measure what is the signal can be received by this standard gain horn. Okay, and the gain values of this gain horn can be found on the data sheet. Then we put our antenna back onto these mounting stations and to measure what is the signal level can be received by our antennas. Then compare the signal level of our antenna and this standard gain horn, we can calculate the gain value of our antennas. Okay, so that is one type of measurement. In that measurement, both transmitting antenna and receiving antennas, they are fixed. There is no rotation involved. Okay. The second type of measurement is called radiation patterns. So radiation pattern, that means we're trying to measure the radiation strength of our antenna with respect to angles. So that is why we put a rotator here. Okay. So basically, the software installed on computer will control the rotation of this station. Okay. Let's say for every half degrees, we take a measurement for. Okay, then when we take a entire 360 degrees, we can get plot. So that plot will tell you the receiving capability of our antenna in different directions. So the last measurement we can measure here is to measure the axial ratio if your antenna is a CP antenna. Okay, of course this is not a CP antenna, this is a linear antennas. But if we install a CP antenna here, we want to measure the quality of the circular polarization generated by your antennas. Okay, in that case, instead of rotate these stations, okay, there's a feature on the transmitting side to rotate the polarization of the transmitting horns. Okay, so let's go back to take a look. So there is a rotation mechanism installed here. As you can see, this antenna is able to spin in this direction. Okay, so this is a linear polarized antenna. So it generates an electrical field from in this direction, from this long edge to this long edge. So when we manually rotate the angle of the polarizations, okay, the level of the signal you received from a CP antenna at the other end will change. Okay, if your antenna is a perfect CP antenna, then the signal level will not change. So you will get a perfect CP antennas. However, in real life, never get a perfect CP antennas. So based on the signal level change with respect to the rotation of this linear polarized antennas, we can calculate the actual ratios. Okay, that's all for this measurement. And here I give you a list of the publications we published in recent years on this SIEW research work. And I will thanks to all my graduate students who involved in this research. And I welcome any questions. So I only get one question. Someone asked if this video will be posted on our website for future reference. I don't know. Maybe we need to ask the IT persons. Maybe they have a plan to post it or not. Okay. So I got another question. Daniel asked the question: does this do anything to improve line of sight issue in antennas? So line of sight issue in antennas, I'm not sure what you are talking about. So like so depending on the applications, right? Some like for example for terrestrial microwave, you have fixed antennas. Then antenna the dominant path is line of sight. But in urban areas, you have multiple reflection and multi-pass. Okay, so I like to point out the problem we're solving here is we're trying to solving how to design antenna at higher frequencies because the 5G system use higher frequencies. And the structure we invented will be a good candidate for millimeter wave applications, for example, 5G systems, because it will give you increased efficiencies. Okay. Another question is maybe you can discuss the scaling of antenna so it can be applied to 5G. Yes, as I mentioned, the antenna is the frequency scaling property is a general rule. Okay, it's generally true for any antennas. So the antenna we designed here is operating around the frequency around 20 gigahertz. Okay, so if you want other frequencies, you can just simply do the frequency scaling. Okay. However, there are some practical issues when you do the frequency scaling. For example, like the input ports, the SMA, you cannot scale. Okay. So after the frequency scaling, there is some optimization you need to run to solving the problems. I have another question here. Okay, I got the answer about the presentation from IT person. He said the presentation will be available online. Let me answer the last question. Brian Martinson mentioned, said, you mentioned Internet of Things, like autonomous vehicle. You also mentioned independent signals, vertical and horizontal. Does each device in such a vehicle need a different signal? And how do you isolate? That is there enough space? Yes, normally, first of all, okay, the frequency is the resources. You acquire frequency from FCC and you pay money to FCC. And depending on the band, and sometimes when FCC assign you a band, they specify the polarizations. For example, if they only specify vertical polarization, then you can only use vertical polarizations. Okay, but if FCC allows you to use both vertical and horizontal polarizations, why not use both of them, right? Because you already paid money. If you purchased both polarization but only use vertical polarization, then you are wasting your money. Isolation of signals there are several different ways. Okay. Using different polarization is one way. Another way is the frequency. So although you use a very broad frequencies, but you normally at the back end of RF, they have the digital signal processing part. We call it baseband processing. So for the baseband processing part, you can divide those spectrum into many small slots. Okay, and each device can only use a very small fraction of the bandwidth. Okay. The third way is the time, like in the time domains, you can cut the time scale into different slots and assign to different device or different users. And also for the space, is there enough space? I guess you're talking about the space for putting the antennas. That that depends on like how like when you check iPhone, okay, the iPhone itself, it already have a bunch of antennas. Okay, some antennas for the cellular systems, one antenna for cellular systems, one antenna for iPhone, and some of them also have a separate antenna for example, FM or AM signals if you have a built-in radio inside. So the space is definitely a problem that need engineers to be very carefully optimized and design their whole system. Okay. Vincent Zhang has a question like comment on diversity in terms of polarization, comment on frequency multiplexing in terms of supporting many users. Yeah, I believe I answered that question when I answered Brian Martinson's question. So you have different technology to support multiple users. You can use different polarization, different frequency band, and different time slots, and so on. Okay, I think my presentation is done. Then I will stop my sharing.
Thank you very much, Dr. Wu, for sharing your research project with us. Now, each year, the selection committee reviews many excellent proposals and hears oral presentations before selecting the Douglas R. Moore Award recipient for the coming year. And tonight, I am very pleased to announce that the 2021 Douglas R. Moore Faculty Research Lectureship Award will be shared by two faculty members in the Department of Government, Dr. Scott Granberg-Rademacher and Dr. Kevin Parsoneau. Their presentation will focus on the revolutionizing impact of the internet and social media in American politics, where political figures and candidates are now using social media to sidestep traditional media and communicate directly with voters. So congratulations to all the faculty members who responded to the call for proposals this year. It was an extremely strong pool of applicants. And as you know, the Douglas R. Moore Award recipients are interviewed and selected by a committee of past award recipients. And I want to thank this year's selection committee members and the committee chair as well, Dr. Gwen Westerman. That concludes this evening's event, and thank you all for joining us.